Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The intellectual landscape of theoretical physics in the mid-20th century presented a profound and stubborn puzzle, the nature of continuous phase transitions and critical phenomena. While thermodynamics provided a grand framework for equilibrium states, its machinery faltered at the precipice of change, at the critical point where, for instance, a liquid and its vapor become indistinguishable or a magnet loses its spontaneous field. Here, physical quantities like specific heat and magnetic susceptibility diverged, exhibiting singularities that defied the elegant, analytical approaches of the time. The prevailing framework, the mean field theory pioneered by Lev Landau, offered a beautiful and intuitive picture based on an order parameter, yet it yielded incorrect predictions for the critical exponents that characterized these divergences. Landau's theory, in its smoothing of spatial fluctuations, overlooked the very essence of the critical point, the emergence of correlations across all length scales. The correlation length, a measure of the typical distance over which microscopic degrees of freedom are correlated, itself diverges, rendering the system a complex, self-similar fractal. The challenge, therefore, was to create a theoretical edifice capable of handling the physical system with an infinite number of strongly interacting degrees of freedom at every scale. It was into this perplexing environment that Kenneth Wilson introduced his formulation of the renormalization group, a conceptual and computational synthesis that fundamentally altered our understanding of physical reality, revealing a hierarchical structure to natural law and providing the definitive solution to the problem of critical phenomena. The genesis of Wilson's breakthrough lies in a confluence of ideas from statistical mechanics and quantum field theory. The intellectual inheritance began with the phenomenological scaling laws of Benjamin Wirdum and others, which observed empirical relationships between the various critical exponents. These laws strongly suggested a deep, underlying homogeneity and symmetry in the thermodynamic potential near the critical point, but they remained descriptive observations awaiting a causal explanation. The most direct conceptual precursor to Wilson's work came from Leo Kadanoff in 1966. Kadanoff envisioned a process of block spins, a Jerdon-Ken experiment where one would group a block of atomic spins in a magnetic model, like the Ising model, and replace it with a single, new block spin. The hope was that the physics of the system of blocks would resemble the physics of the original system, albeit with rescaled or renormalized coupling constants. This intuitive leap contained the seed of the renormalization group idea, the system's properties are self-similar under a change of scale. Kadanoff's hypothesis elegantly pointed towards the origin of scaling laws but lacked a systematic, calculable procedure to implement this coarser-graining and determine how the interaction parameters would indeed transform. The problem was further compounded by Wilson's own background in quantum field theory, a domain plagued by its own divergences. In QFD, calculations of physical quantities often produced infinite results, which were tamed through a formal procedure also called renormalization, developed by luminaries like Richard Feynman, Julian Schwinger, Shinichiro Tomonaga, and Freeman Dyson. This procedure involved absorbing infinities into a redefinition of fundamental parameters like mass and charge. While functionally successful, its physical meaning was opaque. Wilson, steeped in the formalisms of QFD and grappling with the strong interactions via the work of Murray Gell-Mann, possessed a unique perspective. He recognized that the divergence of the correlation length in statistical mechanics was analogous to the problem of a field theory with massless particles, and that the techniques of field theory might furnish the missing calculational framework for Kadanoff's beautiful physical intuition. The work itself, articulated in a series of seminal papers in the early 1970s and comprehensively reviewed with John Coggart in 1975, presented a concrete realization of this vision. Wilson's crucial insight was to formulate the problem in the space of all possible Hamiltonians. The renormalization group is a transformation, an operation that maps one Hamiltonian to another. He first developed a momentum shell integration technique. One begins with a system described by a Hamiltonian, such as the Ginzburg-Landau-Wilson free energy functional, expressed in terms of its Fourier modes in momentum space. The transformation proceeds in two steps. First, one performs a coarser graining by integrating out the high momentum, short wavelength modes of the system. These modes correspond to microscopic fluctuations over small distances. This step is the mathematical implementation of Kadanoff's blocking idea. The second step is a rescaling of momenta, coordinates, and fields to restore the system to its original appearance, effectively zooming out to view the system at a larger length scale. The result of this two-step process is a new, effective Hamiltonian for the remaining low momentum modes, but with transformed coupling constants. The core of the method is to study the flow generated by the repeated application of this transformation. This RG flow charts a trajectory in the infinity-dimensional space of Hamiltonians. This picture leads to the central, organizing concepts of the theory. A critical point of a physical system corresponds to a fixed point of this RG transformation, a special Hamiltonian that maps onto itself under the flow. The behavior of the RG flow in the vicinity of a fixed point explains the entire phenomenology of critical phenomena. The transformation can be linearized around a fixed point, and the stability of the flow is determined by the eigenvalues of this linearized transformation. Hamiltonians are described by a sum of operators, each multiplied by a coupling constant. The couplings associated with eigenvectors having eigenvalues greater than 1 are called relevant. These couplings grow under the RG flow, pulling the system away from the fixed point and dominating the long-distance, macroscopic physics. Couplings with eigenvalues less than 1 are irrelevant. They shrink under the flow, meaning the corresponding microscopic details of the system become unimportant at large scales. Couplings with eigenvalues equal to 1 are marginal, and their behavior requires more delicate analysis. This framework provides the profound explanation for the phenomenon of universality. Different physical systems, such as a ferromagnet, a binary alloy, or a liquid gas system, may have vastly different microscopic Hamiltonians. However, if they flow towards the same fixed point under the renormalization group transformation, the long-distance critical behavior will be identical. Their macroscopic properties are governed solely by the small number of relevant operators at that fixed point, which in turn are determined by the dimensionality of space and the symmetries of the order parameter. The myriad non-universal, irrelevant parameters describing the specific atomic interactions are washed away by the flow. To make this powerful conceptual framework a calculational tool, Wilson introduced the ingenious epsilon expansion. He observed that in 4 spatial dimensions, the predictions of mean field theory become correct by performing calculations in a dimension written formally as 4 minus epsilon, where epsilon is a small parameter. He could develop a perturbative expansion in epsilon to compute critical exponents for the physical case of 3 dimensions. This brilliant maneuver turned an intractable non-perturbative problem into a solvable one, yielding values for the exponents in stunning agreement with experimental measurements. The immediate impact of Wilson's work was transformative and definitive. For the first time, physicists could calculate critical exponents from a fundamental theoretical basis. The long-standing puzzle of why the exponents for the specific heat of liquid helium near its lambda point were so close to those of the magnetic susceptibility of the 3-dimensional Ising model found its answer. Both systems belong to the same universality class, their RG flows terminating at the same fixed point. The epsilon expansion provided a systematic way to compute these universal quantities to high precision, resolving decades of theoretical frustration. Michael Fisher, a key figure in the field, quickly championed and elaborated upon Wilson's ideas, helping to disseminate them throughout the statistical mechanics community. The Renormalization group provided a dictionary, a Rosetta Stone, that translated the microscopic details of a system into its macroscopic critical behavior. With universality as the guiding grammatical rule, the success was so complete that it effectively closed the book on the foundational problem of continuous phase transitions, shifting the research frontier toward applying this powerful new way of thinking to other complex problems. The very language of physics began to change, with notions of fixed points, relevant operators, and RG flows becoming standard conceptual tools for a generation of theorists. The subsequent evolution of Wilson's ideas demonstrated their remarkable breadth and power, extending far beyond their initial application in condensed matter physics. The renormalization group concept was, in a sense, returning home to quantum field theory, but it did so with a new, profound physical interpretation. The old view of renormalization in QFD was a mathematical prescription for hiding infinities. Wilson's RG reconceptualized quantum field theories themselves as effective field theories. A theory like quantum electrodynamics is a low-energy description of reality, valid up to some momentum cutoff. The parameters we call fundamental constants, like the electron's charge, are in fact running couplings whose values depend on the energy scale at which they are measured. The RG flow describes this dependence. This perspective was canonized by Steven Weinberg and others, becoming the bedrock of the modern understanding of the standard model of particle physics. Perhaps the most spectacular application occurred in the theory of the strong nuclear force, quantum cryodynamics. In 1973, David Gross, Frank Wilczek, and David Politzer used the renormalization group to analyze the behavior of the coupling in a non-abelian gauge theory like QCD. They discovered that, unlike in QED, the strong force coupling constant becomes weaker at higher energies, or shorter distances. This property, known as asymptotic freedom, explained why quarks behave as nearly free particles inside protons and neutrons when probed in high-energy scattering experiments. The calculation was a direct application of Wilson's RG formalism, and it was the key theoretical breakthrough that solidified QCD as the correct theory of the strong interactions, a feat for which they received the Nobel Prize. The influence continued to spread. Wilson himself used a numerical implementation of the renormalization group to provide the first complete solution to the Kondo problem, another long-standing puzzle in condensed matter physics concerning the behavior of a magnetic impurity in a metal at low temperatures. In the 1980s, Alexander Polyakov and Alexander Zamolodchikov would show that the principles of the renormalization group are central to two-dimensional conformal field theory, which forms the mathematical basis of string theory. The beta function, which governs the RG flow of coupling constants, must be zero for a consistent string background, making search for fixed points a central activity in string theory. The reception of Wilson's work was initially complex, reflecting its radical departure from established methods. To many physicists trained in traditional perturbative techniques, the initial formulations appeared physically obscure and lacked the mathematical rigor they were accustomed to. The idea of an infinity-dimensional space of Hamiltonians and flows within it was a difficult conceptual leap. A certain irony attended its early years. A technique whose name derived from a procedure to handle infinities in field theory was now being used to explain observable singularities in statistical mechanics. In doing so, it ironically provided the first truly physical explanation for the field theory procedure itself. The conceptual elegance of the RG, however, was undeniable, and its spectacular calculational successes quickly overcame any initial skepticism. The community, led by influential figures like Fisher and Kadanoff, rapidly embraced the new paradigm. Over the following decades, mathematicians such as Jean Mitchell-Bismuth and physicists like Krzysztof Gordsky and Antti Tupiainen worked to place the renormalization group on a completely rigorous mathematical footing, solidifying its foundations and proving the existence and properties of the RG flows that Wilson had posited on physical grounds. The critiques faded as the successes mounted, and the renormalization group evolved from a clever technique into a fundamental worldview. It influenced not only specific calculations, but so the very style of inquiry in theoretical physics, promoting a non-perturbative, scalar-dependent way of thinking about physical. In conclusion, Kenneth Wilson's development of the renormalization group stands as one of the deepest intellectual achievements in 20th century physics. It resolved the stubborn problem of critical phenomena by providing a framework that both explained the universal, simple behavior observed at large scales and accommodated the complex, non-universal details at microscopic scales. Springing from the intuitive ideas of Leo Kadanoff and armed with the formal power of quantum field theory, Wilson's synthesis gave us the language of fixed points and relevant operators, a language that has become indispensable across physics. Its application by Gross, Wilczek, and Politzer to establish asymptotic freedom in QCD demonstrated its power to solve fundamental problems at the highest energy scales, just as Wilson's own work had solved them at the lowest energy scales of condensed matter. The influence pervades modern theory, from the structure of the Standard Model to the foundations of string theory, through the work of figures like Weinberg and Polyakov. Wilson's legacy is a profound shift in perspective. He taught the world of physics that physical laws are not monolithic and immutable, but are instead hierarchical and scalar-dependent. The theory that describes a water molecule is different from the one that describes the boiling of water. Yet, the renormalization group provides the bridge that connects the two. It is more than a tool, it is a statement about the structure of knowledge itself, a lasting testament to the idea that changing one's point of view can, in fact, change the world.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.